We now turn to some very special vocabulary, trans versus cis. See, if you have a ring with two substituents, if the two substituents are going in the same direction, either both up or both down, then it is called a cis ring. If they're going in opposite directions, then it's called a trans ring. Let me show you some examples. In this example right here, we can see that we have two chlorines that are stuck on a cyclohexane. Now remember, when we see a dashed bond like this, it means that these bonds are going three-dimensionally down. You'll notice that both of these chlorines are both pointing down. Because they're both pointing in the same direction, down, this would be called a cis 1,2-dichlorocyclohexane. And these two substituents, these two chlorines, are cis to each other. Let's look at this example over here. You'll notice that these two chlorines are both pointing up. Yes, this wedged bond means that these atoms are pointing three-dimensionally up relative to the plane of the slide. Because both of these atoms are both pointing up, we also can say that they are cis to each other. Hence, this molecule is also cis 1,2-dichlorocyclohexane. Now, parenthetically, you might not believe me, but these two molecules, the one on the left and the one on the right, are actually exactly the same. If you could imagine taking this molecule right here and flipping it upside down like a pancake, both of these chlorines would swap places and their bonds would both be dashed going down. These two molecules would therefore look and therefore are exactly the same. Now here are two other examples. You'll note that in this example, the chlorines are pointing in opposite directions. One is going up and one is going down. In this example, this one is going down and this one is going up. Because the two substituents on the ring are going in opposite directions, these rings are called trans rings, and these substituents are trans to each other. Now, one thing that I want to point out is the substituents do not have to be in a 1-2 relationship to each other on the ring. I happen to draw them that way, but these chlorines could be in a 1-3 or a 1-4 relationship, or a 1-3 over here or a 1-2 relationship over here. And if they were, as long as they're pointing in opposite directions, it would still be a trans ring. And if they were pointing in the same direction, it would still be a cis ring. So this brings us to a question from our problem set. Draw trans 1,2-dibromocyclohexane in a chair structure format. To do this problem, we have to understand how to convert our two-dimensional flat structure, which is shown here, into our semi-3D chair structure. And how do we do that? Well, the first thing that we have to do is realize that when we look at this flat structure, every time we see a wedged bond like this one, it means that this bromine is three-dimensionally pointing up, and every time we see a dashed bond like this one, it means that this bromine is three-dimensionally pointing down. Now that we have that concept down, the next step is to number all of the carbons in the ring. Now the purpose of doing that for this problem is just to establish reference points. So it doesn't technically matter for this specific type of problem what numbers you assign to each position. For our case, I'm going to assign them these numbers here. 1, 2, 3, 4, 5, and 6. Now the next step is to draw our chair. Although we could draw either of the two possible chair structures that I showed on an earlier slide, the regular chair or the mirror image bow tie, I've chosen to draw the shape shown here. We now number each of the carbons in our chair structure so that we can connect it to its corresponding carbon atoms in our flat structure shown at the left. So here we go. 1, 2, 3, 4, 5, 6. And what do we do now? Well, now we draw each of our axial and equatorial bonds. Now we don't have to draw them at every single position on our chair unless we happen to be some kind of overachieving Hermione Granger or something. We just have to draw them at the positions that have the bromines on them, which are positions 1 and 2. So I'm going to go ahead and just draw the bonds on positions 1 and 2. The axial bond on atom 1 goes straight up, and the axial bond on atom 2 goes straight down. The equatorial bond goes at an angle down on atom 1, and the equatorial bond on atom 2 goes at an angle up. So what do we do now? Well, now we have to ask ourselves, where do our bromines go? Now to answer this, we first have to answer the question, are the bromines pointing up or down in each position shown in the structure to the left? On carbon 1, you'll note that bromine is attached to a wedged bond. Therefore, it is pointing up. So which of the positions here on 1 should it be attached to? Should it be attached to the axial position or the equatorial position? You'll note that the axial is pointing up and the equatorial is pointing down. So the bromine, because it's going up over here, should be pointing up over here, and that is indeed where we put it. Hence, the other position is the hydrogen that is bonded to carbon 1. As we look at carbon 2, you'll note that there is a dashed bond attached to this bromine, which indicates that this bromine is pointing down. We look over here at carbon 2 in our chair. Which bond is pointing down? Is it the equatorial or is it the axial? Of course, you can see it's the axial, so the bromine had better be pointing down. And in this particular example, it is on the axial position. The hydrogen that's attached to carbon 2 therefore goes in the equatorial position relative to the bromine. Now I need to pause and point out that some students think that because the equatorial position is the more favorable, that means that you always need to put your atoms in the equatorial position in this type of problem. Now that isn't true. You put them wherever they happen to go, be they equatorial or axial. What determines whether they go equatorial axial? It's all based on whether they're pointing up or down. Now you'll notice that once again this bromine is pointing up, and the up position on carbon 1 over here happens to be axial. This bromine attached to carbon 2 happens to be pointing down, and the bond that's pointing down on carbon 2 happens to be axial. Hence, this bromine over here goes up on the axial, and this bromine down here goes down on the axial, not equatorial. Because if they were equatorial, we'd be having the opposite configurations here. Now, I know that in looking at this particular structure, you might be thinking, this doesn't look very good. Is there any way that I can put these two bromines in the equatorial position? Yes, there is. The easiest way is to just change by one position clockwise or counterclockwise the original location of our numbers. Now, I've gone ahead and done that here. Because the location of our original numbers is arbitrary, it doesn't really matter where I put them in the diagram shown here to the right, as long as I number them in the same direction, either clockwise or counterclockwise, as I did on the left. At this point, I can now draw my axial and equatorial bonds. Let's look at carbon 1. You'll note that it's pointing down, so my axial position should be pointing down, and the equatorial should be pointing at an angle up. On carbon 2, the axial bond should be pointing up, and the equatorial pointing at an angle down, and indeed that happens to be the case. As before, we don't have to draw axial and equatorial bonds at every single position in the chair, unless we want to be brown-nosing Poindexters. Instead, we just draw them on the positions that have the bromines on them, which are positions 1 and 2. Now we have to ask ourselves, where do our bromines go? Once again, to answer that, we first have to ask, are the bromines pointing up or down at each position in the structure shown on the left? You'll notice that the bromine here attached to carbon 1 is still pointing up. Let's go over here to carbon 1 and ask ourselves, which of these two bonds is pointing up? Is it the axial or is it the equatorial? Well, the axial is pointing down, obviously. The equatorial is pointing up. Hence, the bromine had better go in the equatorial position, and the hydrogen by default goes down on the axial. Now let's look at this bromine. You'll notice that it's attached to a dashed bond, which indicates that it's going down. It's attached to carbon 2. So which bond is going down on carbon 2? Is it the axial or is it the equatorial? Well, of course, the axial is going up and the equatorial is going down. Hence, the bromine had better be on the equatorial position going down and the axial going up. One thing that I've seen students sometimes get confused about is they see the equatorial bonds that are pointing up or down, and they think, now this isn't really up or down because it's not pointing as up as an axial up is. Or this isn't really down because it's not pointing down as much as an axial down is. That is a load of garbage. This is an equatorial up. I realize that it's not pointing straight up the way an axial up is pointing, but it's still totally up. And this is an equatorial down, and I realize it's not pointing down as starkly as an axial down, but it's still totally down. Hence, this is a correct chair conformation drawn of this. And you'll notice that it places both of the bromines in the equatorial positions, which are the more stable positions.
With that said, let's go to an example problem.
Which of the following represents the most stable chair conformation of the molecule shown in the box below? Now, to answer this question, I'm going to first number every atom in my original cyclohexane ring. Now that I've done that, I want to focus on the positions and directions of each substituent on the ring. Note that my tert-butyl group over here is on carbon 1 and it's pointing down. My chlorine atom, which is up here, is on carbon 3 and it's also pointing down. And this ethyl group is attached to carbon 5 and is pointing up. I can tell that because these are dashed lines and this is a wedged line. Now let's look at our multiple choice examples. If I look over here, my tert-butyl group is pointing down, my chlorine is pointing down, and my ethyl group is pointing up. Does that match what I saw? Tert-butyl going down, chlorine going down, and ethyl up? Yeah, it does. So A is a possibility. Let's look at B. My tert-butyl here is also going down. It's equatorial down, which doesn't look quite as down as an axial down, but it's still totally down. It's down. Look at this chlorine. It's also going down, and this ethyl is going up. So I've got down, down, up. Does that match? Down, down, up. Yes, it does. Let's look at option C. I've got my T-butyl going down, my chlorine going down, and my ethyl going down. All three of them are going down. Does that match? No, it doesn't. Hence, C is not a correct chair drawing of this particular structure at all. Let's look at option D. In option D, I've got my T-butyl going down, my chlorine going up, and my ethyl going up. So I've got down, up, up. Does that match? Absolutely not. So this is also not a correct chair drawing of this particular molecule. So the only two contenders that are correct chair drawings are option A and option B. The question asks us to choose which of them is the most stable one. Which one do you think is? Well, as I mentioned earlier, the equatorial position is more favorable, especially for large groups like this T-butyl group. In this particular example, B, I've got a tert-butyl that's equatorial, a chlorine that's equatorial, and an ethyl that's axial. In option A, I've got a T-butyl that's axial, a chlorine that's axial, and only an ethyl that's equatorial. Hence, between the two of these, B is much more stable and is the correct answer.